Hi children, so today our topic is resistors in parallel. Last session we have seen resistors in series, that what is the equivalent resistance or effective resistance when three resistors or any number of resistors are connected in series. Now let us move on to the topic resistors in parallel. So first let us understand what a parallel connection of resistors look like. So for that we have to consider three resistors of different values of resistances R1, R2 and R3 which are connected in parallel. So a parallel connection goes something like this, where the same terminals are connected together and the other end are connected together. So it's like it is analogous, or it is similar to a situation where people are standing one in front of the other, and where the right hands of all the people are connected or held together and the left hands are held together. So you can think of people standing in a column. Series was you have to consider as standing in a row. So this is the right hand and left hand, right left, and if you join the all the right hands together, that is if you hold the right hands of all of these three people, if these three people are held together and the left hands are held together, then that looks like a parallel combination. So coming to this figure, when it comes to the resistors R1, R2 and R3, you can see the, if you consider this as the positive ends, actually resistors are can be considered as wires of different lengths or different area of cross section, such that its resistance is different. It doesn't have a positive end and negative end, but whatever goes into the positive terminal of the battery can be considered as the positive end of that resistor, and whatever goes into the negative terminal of the battery can be considered as the negative end. So as such, resistances do not have any positive end or negative end, just like a cell has. Okay, so here you can consider as this cell is connected to the positive end, so these can be considered as the positive ends of these resistors. So they all are connected together, and as the negative end goes to this side, that can be considered as the left side can be considered as the negative end. So this is the parallel combination of resistors. It can also be represented in several ways. It can be shown like this also. You need not show it as a box. It can be shown like this also, where this is also a parallel combination. That is all the common ends are connected together and the other ends are connected together. Now you can see an arrangement to measure the potential difference. Now what is the device used to measure the potential difference? It is a voltmeter, and you can see the voltmeter is connected in parallel to this combination. So this is a parallel combination of three resistors. Again, a voltmeter is connected parallel to this combination in the sense that it is connected to the common ends of the three resistors. Okay, now its duty or its role is to find out the potential difference in the across the resistors, combination of resistors. Now you have another device which is known as the ammeter, which is connected to measure the current flowing through the circuit. Okay, current flowing through the whole circuit. Now we have a cell, a group of cells or battery in order to send the current through the circuit, and also we have a key which is in closed position, so that I have put a dot in the center. Now let us look at the current which is flowing through the whole circuit. Now in a parallel combination, what you have to notice is that the current flowing is same. That is I is different. I is different in parallel combination, but potential difference V. This is current I is different in parallel combination, but potential difference is V is same across each component. So this is the important point to be noted. I varies, but V remains constant in a parallel combination. So that is what we have to memorize or remember in when you consider the case of parallel combination of resistors. So you have I as different in parallel combination, but V is the same. Now let us look at this. I goes here. Now it gets split into I1, I2 and I3. As I told you, I is different across each component or across each resistor. So I splits into I1, I2 and I3. And after coming here, it will again join and it will become I again. Okay, I is the current flowing through the whole circuit. Now, this can be considered as a situation where you have a pipe which is being connected to three different pipes. Okay, so what will happen to the water flowing? Water flowing from here will split into these three pipes. So you can consider this as the current flowing, the main current being flowing through the main circuit, and the you can see it is being split into I1, I2 and I3. Okay, now again if you join it here, again it will be the total current passing through it, or the total water which is flowing through it. Okay, now we have to write the equation in terms of the varying quantity which is current. So let us write the current across each component separately. So first let us write I1. I1 will be equal to, according to Ohm's law, it is potential difference divided by the resistance. Potential difference is same, so we can represent it by V divided by R1, and I2 is equal to V divided by R2, and I3 is equal to V divided by R3. So we got three equations for the current flowing across R1, R2 and R3 respectively. Now we also know that the total current will be the sum of the current through each of the components. So you can write I is equal to I1 plus I2 plus I3. What is I? I is the total current which is coming from the battery. Now that can be represented as I is equal to V divided by Rp, where Rp is known as the equivalent resistance of the parallel combination. So that will be equal to the potential difference divided by the equivalent resistance. That is, if you were to replace R1, R2 and R3 by some resistance, that resistance is represented as Rp. Now we can add these equations I1, I2 and R3, I3 as, we can write it as V by R1 plus V by R2 plus V by R3. That is as per the equation I1, I2 and I3, which is equal to I equal to V by Rp. V by Rp. Now you can take V outside, so it will become 1 by R1 plus 1 by R2 plus 1 by R3. Isn't it? V gets cancelled. What you get finally is 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This gives you an expression for the equivalent resistance of the parallel combination of three resistors of varying resistances R1, R2 and R3. So this is the expression for the equivalent resistance. Now let us analyze certain factors here, what all we need to consider when it comes to a parallel combination of resistances. So you can easily find out that how can you define the equivalent resistance in parallel combination? You can say that the reciprocal of equivalent resistance in parallel combination is equal to the sum of reciprocals of individual resistances. That is, if you have any number of resistances being connected in parallel, then the reciprocal of the equivalent resistance will be equal to sum of reciprocals. So it is a reciprocal relation, not like, unlike the case of series combination, which was simply the sum of individual resistances. Here we have a reciprocal relation which says that 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Now we can just find out the case of a simple case where we have connected 1 ohm, 2 ohm and 3 ohm in parallel. So say R1 is 1 ohm, R2 is 2 ohm and R3 is 3 ohm. Then what will be Rp? Or the equivalent resistance? It will be 1 by Rp is equal to 1 by 1 plus 1 by 2 plus 1 by 3. Now you have to, if you have to add this, you have to add, go for the LCM because they are fractions. So it is 1 plus 1 by 2 plus 1 by 3. So the 2 into 3, 6 is the LCM. So 6 plus 1 into 3 is 3, 1 into 2 is 2, so it is 6 plus 3, 9, 9 plus 2 is 11, 11 divided by 6 is 1 by Rp. Okay, this is 1 by Rp. Now, this is not RP. So, if you want to get RP, you have to take the inverse of this. So, RP is equal to 6 by 11 ohm. So, 6 by 11 ohm will be anyway lesser than 1 because it is a fraction. And you can see that this is a value which is less than 1. When you compare this value, the equivalent resistance with each of the resistors connected or the resistances connected, 1 is the lowest value here. 1, 2 and 3, this is the lowest value. You have got a resistance which can be replaced by these three, which is lesser than the lowest value. So in the case of parallel combination, you can note that point that equivalent resistance RP will be less than lowest value among the combination of resistances in parallel. So this is what happens in a parallel combination. The resistance considerably decreases, that is, it becomes lower than the lowest value. So if you are going to connect a 1 ohm and a 100 ohm resistors in parallel, you are going to get a resistance which is less than 1 ohm only, because you are going to go for this equation 1 by Rp is equal to 1 by R1 plus 1 by R2. So if whatever resistances you connect, if you want to reduce the equivalent resistance or the effective resistance, you can go for a parallel combination. So if you want to reduce, so what happens when the equivalent resistance is reduced? What happens is the current flowing through the circuit increases when compared to the current flowing through each resistances when it was individually connected. So you can note that point also in a parallel combination. So if ever you want to reduce the resistance, then you can go for parallel combination. So you can say that the equivalent resistance RP reduces and current I increases when compared to current when any one of this resistance is connected. Okay, so in a parallel combination, as the resistance reduces, the current increases considerably. So if you consider the current flowing across R1 alone, if R1 was the only resistance in a circuit, then when you make a comparison between a parallel combination, so if any two resistors are connected in parallel, then it is going to reduce below the individual value of the resistances, and the current is going to increase. So in a parallel combination, you can have the current is varying, I varies and V is same. Then you will be wondering, as I is split into these three values of current, I1, I2 and I3. From here it is splitting. So you will be wondering why we have not considered the current across the voltmeter. For the reason for that is actually it is a little beyond your the scope of the syllabus, but I can give you that information for students who are really thoughtful about that thing. You will be thinking why the current across the voltmeter is not considered, because voltmeter is also working in this circuit. So the reason is a voltmeter is a device of very large resistance. That means the current flowing through a voltmeter will always be negligible. Actually, they are two opposite kind of instruments or devices. A voltmeter has very large resistance. It's a device with very large, even these devices are constructed on the basis of some principle, and they will be having an appreciable amount of resistance. So voltmeter has very large resistance, and an ammeter has very low resistance, because it should make the current flowing through it as maximum, because it is a device shown for the measurement of the current. So it should have a very low resistance, because the current flowing through the circuit should completely pass through the ammeter to show the deflection. Okay, and the voltmeter has very large resistance. When resistance is very large, the current flowing through it can be considered as negligible. You don't have to consider the current flowing through a voltmeter. So I varies, V is same. And another thing to be noted is, if you want to reduce the resistance, then you can go for parallel combination. Suppose if you have identical resistances means all the resistances having the same value of resistors. So you can consider R1 is equal to R2 is equal to R3 is equal to R. That means they are identical. You have heard about identical twins, no? Identical twins means they look alike. So in this case, the resistance, their characteristic is resistance, so they have the same resistance, so it can be represented by R. We have written R1, R2, R3 in order to identify them as separate. So if all are alike, then you can simply write it as R. So if three identical resistors are connected in parallel, identical resistors in parallel, then what will be the parallel combination? 1 by Rp is equal to 1 by R plus 1 by R plus 1 by R, which is equal to 3 by R. Denominators are same, 1 by Rp. So that is equal to Rp is equal to R by 3. So the equation becomes again very, very simple. That is, you just have to divide the individual resistance with the number of resistors you have connected if they are identical. If you have n number of resistors, they are identical, then you can easily write the equation as Rp is equal to R by N. If it is 5 resistors, then it will be R by 5. If it is 10 resistors, then it is R by 10 and so on. So this is the case which is related to parallel combination of resistors when they are different. So the drawing the circuit diagram is very, very important. You have to keep certain things in mind in order to draw the circuit diagram, and start writing the equation in which the quantity varies. Here the current varies, but the potential difference remains the same. And there are certain, now as we have understood what a parallel combination is and what a series combination is, you can you will be now able to solve any kind of network which has a combination of series as well as parallel. That is, in a single network, see, this we have seen as separate, isn't it? One circuit we had only series. Now in the other circuit we had parallel. But it can also happen that you will have a network of resistors where one is connected in series with the parallel combination of other resistors. So that can also, we can also discuss such circuits and how to find the equivalent resistance in a particular circuit. Now let us see, there are certain advantages and disadvantages which is related to parallel combination and series combination. First, let us discuss the case of series combination, which has many disadvantages. The thing is that in series combination, we have the current. In series combination, we have I as same. I is same. That is, the same current is flowing through the each of the component, but V is different. V varies. That is, V varies means there is a potential difference across each component. So what happens is, if you connect any three devices in a series, say if you have a wire, then you have a bulb, or you have any other component, say an electric toaster. So each one will be having different resistances. What happens is, the potential difference across each component will be different. So across R2 is V2, across R3 is V3, and across R1 is V1. So as the potential difference is different, they don't get the correct amount of potential difference for its correct operation. It doesn't get the correct operating voltage across which it is corrected, because it is being shared among each other, isn't it? Because one single battery is connected across these, or any kind of supply is connected across these three resistances. So what happens is, the potential difference is shared among them. So it is not able to work properly if it is connected in a series connection. Now another thing is that as current flowing each of the component is same, if any one of the component goes faulty, or if any one of it becomes if say these are three devices which has been connected in series, if the bulb gets fused, what happens, this current gets blocked, or the current is not able to pass on to the next component. So the current flowing through the circuit stops, and this circuit becomes a defective one if any one of it goes faulty. So that is another disadvantage of series connection. So you might have seen decorative lamps which are connected. They actually small bulbs which are connected as a decorative item. In that those bulbs are in series connection. So if any one of the bulb goes faulty, then it is very difficult for the person to find it out and to restore the connection easily. So that is one disadvantage of series connection. Then one advantage is that you can see is that the resistance increases considerably and the current flowing through it decreases considerably. So if you want a very little current to be drawn from a device, then you can go for from very little current to be drawn from the supply, then you can go for series connection. But coming to parallel combination, it is a very there are several advantages over series connection. That is, a parallel combination of resistances always have an advantage. The first one is that I is different. I is different, or current flowing through each component is different. V is same. So they don't have to share the potential difference. Whatever is supplied, actually potential difference is the energy supplied for the electrons to move across the particular section of the a circuit. So they all get the same potential difference, or they can operate at the same operating voltage. But as I is different, that is current flowing through any of the section is different. So if you have any three resistors in combination, in parallel combination, R1, R2, R3, if any of this goes faulty, nothing will happen. It is not going to affect the total or the entire circuit, because only the current flowing through across this section will get cut off. The current will be still flowing through the other two components, and it is not going to affect. So usually in domestic circuits, we have parallel combination. All these are connected to a single source of power supply, and the devices can operate drawing the necessary amount of current from the potential difference or the voltage source. So these are the advantages of parallel combination.